Something you can learn about me at the start of this video is the fact that I own the world's worst Thesaurus. Not only is it awful, it is also awful. Anyway, you probably have to work that one out. 3.1.2.2, it's still paper 1 for this. It's the living world section. We'll have a little look at tropical rainforest. Looking at the specimen assessment materials for 2018, it looks relatively likely a question on tropical rainforest will come up, as so much of the specimen materials have been on deserts. So it's quite likely this will come up. We'll try and cover the top 3 in this video with a bit more of a focus on the third bullet point, plants and animals adaptations, on the basis that that's the most likely question. So locations of the tropical rainforest, with some needless animations coming up as well. Hopefully we can identify this from a previous video in your previous talk classes in year 9 and year 10. Tropical rainforests are generally found close to, if not on the equator, and certainly between the two tropics. Your largest tropical rainforest is the Amazon basin, found in South America, and hopefully you can identify quite clearly there's a real linear distribution here across the equator, with also the Indonesian and the Congo basin as well. Your case study is almost certainly going to be the Solomon Islands, which you can just about make out on this map to the northeast of Australia. In terms of additional points here, you might also identify, if you were asked to describe the location of them, that they generally stretch from the coastline. The reason for their location, really quickly, the equator obviously is an area of the highest concentration of solar radiation, and as a result of that it is incredibly warm. In addition, there's a lack of winds at the equator as air blows towards the equator, and as a low pressure system in tow as well. Winds are very low, it's very warm, a low pressure system formed here as warm air rises, cools, condenses, forms your clouds get to heaven, and it forms what we call convectional rainfall on the equator, and as a result of that it's the ideal conditions for rapid sustained plant growth, and that's why you find tropical rainforest here largely. It is based on the climate, as all biomes are really. Climate is what we call a controlling or limiting factor to the vegetation that you find in any place. So just to recap, on the equator it's very, very warm. As a result you have warm air rising, cooling, condensing, leading to rainfall. Warm and wet are the perfect conditions for plant growth, on the basis that you have around about 12 hours of sunlight a day for high levels of photosynthesis, and the water to sustain that growth as well. So if you're asked that question, between the tropics on the equator, stretching generally from the coastline, is going to be absolutely fine for 3 marks. Largest area, remember, the Amazon basin. In terms of the pattern of climate in the tropical rainforest, this is Manaus, Brazil, which is the most common climate graph used really. If we start with temperature, hopefully you can identify that temperature is a constant here on the climate graph. It's not actually constant, it's very similar throughout the year, I should say. Your lowest point there in January at 26.9 degrees, your highest point at 28.2. That's only a range of just 1.3 degrees across the entire year. So constantly warm. Use those figures, calculate the range. That's the temperature pretty much done. Precipitation slightly more difficult. I would just identify that it's often written that tropical rainforests don't have seasons as such, although actually identifying in Manaus there is a clear drier season than the very wet season. However, just to point out, this is a huge amount of rainfall throughout the year. It's a 2,000mm rainfall throughout the year. With that in mind, we can calculate a very quick range between March 295 down to August at 56, which I believe, doing this very quick off the top of my head, is 239mm range here. I've done this in a previous climate graph video, but just make sure you always check your axes really, really carefully. Make sure you're reading off the right axis. But very wet throughout the year, although there is a clear dry season in August. If you were describing the climate of this area, I would definitely advise you to identify between April and August there is a decline, and obviously from August all the way to December, and actually including January as well, that there is a rising amount of rainfall throughout the year. So warm and wet throughout the year. Right, this is something called the AERS diagram. It's a very, very, very important diagram at GCSE level. It's the idea that this diagram shows the interrelationships, or actually the interdependence as well, I suppose technically, between the different elements of any biome, and in this case the tropical rainforest. Just to take climate first, climate clearly has an influence on vegetation. We'll cover that in a moment through the video. It also clearly has an influence on the soil type. It has the ability to dry the soil, it has the ability to also add moisture to the soil as well. Climate also has an impact on animals. So hopefully at this point you can see the arrows coming off the boxes. Some of them are twofold, which shows that although, as I've just said, climate influences vegetation, actually vegetation also has the ability to influence the climate. Very, very important here in the tropical rainforest. Simply the amount of transpiration caused by the vegetation will actually influence the climate. If you remove the vegetation, there'd be less evaporation and transpiration, which would actually make the climate drier. So hopefully you can see a double link there, whereas climate to soil, actually soil type doesn't really influence the climate on a very large scale, and as a result that would be only a one-way influence. Climate influences soil. Obviously, similar for animals there, really. The vegetation animals influence each other. The soil is clearly influenced by both vegetation animals. As an example, leaf litter dropping to the soil adds nutrients. Feces from animals dropping to the soil adds nutrients. The final section, just to be aware of, I will try and cover it again in this video and possibly a later video as well, is that the rocks do influence the soil type as well, on the basis that rocks weather and break down and can add nutrients to the soil in the same way that animal feces adds nitrogen, potassium, phosphates into the soil, just as vegetation does as well. This is the AERS diagram. If you're not sure about this diagram, the idea of your two links or one link, please come and see us down at H7. It's complicated at first to get your head around this until you simply work out that the arrows simply mean there's a link between them, and that's pretty much all you need to know for that, but it will apply to all biomes. Plants and animals in the rainforest, you probably saw this slide when you went through it. The climate provides ideal conditions for plant growth. Yes, it does. It's very warm and also very wet. This enables plants to photosynthesize rapidly and as a result grow in a very dense fashion. As a result of that, we have a great biodiversity of both plants and animals because of the perfect conditions for growth. It therefore leads to a range of habitats forming because so many different plants can grow here. We've got there up to 100 different plants within a single hectare. That's around about 10 times the amount you'd find in the United Kingdom. As I've previously mentioned, the climate of the equatorial regions is perfect for plant growth, and as a result what you end up with is a whole range of different plant species which have adapted to survive in this climate. Hopefully you've covered this before. The idea on the left there that the tropical rainforest you can organise into different layers, starting from your ground layer, working up to your shrubs, your lower canopy, your upper canopy, and also the emergent layer, the highest of the layers of the rainforest. The idea is that the plants have adapted to survive in these different layers. And the reason for that is simply that the high level of competition means that these plants need to be adapted to survive. I'll go through some of these on the next slide. I'll go through the individual adaptations. For you guys, what you guys really need to know is that these different layers exist on the basis that different plants have adapted to survive at different heights within the tropical rainforest, all linking to this idea of competition, simply on the basis that because this are the ideal conditions for plant growth, your plants must adapt. If they cannot reach the sunlight in the emergent or canopy layer, they must have the adaptation to either survive in the lower tree canopy or indeed shrub layer, or alternatively they would have to adapt to actually make sure they can reach the canopy layer or emergent layer, perhaps without growing in a traditional fashion with roots in the ground and bark and trunks. There may be other ways to reach the sunlight. In terms of the adaptations here, I've got 6 up on the board. What you would need to be able to do on any question that links to plant/animal adaptations is to link it directly to the environment you find the plant or tree within. Taking drip tips is a lovely example. Plants in the United Kingdom generally do not have drip tips. The reason for it is you simply don't need it. there isn't that much rainfall in this country to actually require drip tips to be in place. So if we quickly just run through drip tips in terms of tropical rainforest, actually, vegetation has adapted to have drip tips on the end of leaves. The idea here is drip tips mean that water does not stay on the leaf and quickly runs off. The reason for this is the huge amount of rainfall, over 2,000 millimetres a year, that you would get in any generic rainforest would snap the leaf if it was not removed quickly, so the plant could not photosynthesize and would not survive. Obviously, in this country, there isn't as much rainfall here, so water sitting on a leaf of a plant in the UK isn't going to cause actually a huge amount of damage. In the tropical rainforest, they simply can't afford that to happen because the weight of the water would snap the leaf off. So the trees have adapted, or the leaves I should say, have adapted to ensure that water is removed off them quickly. If we also just do buttress roots quickly, buttress roots, the idea that these are roots actually what would actually be above the ground layer, above the surface itself. A couple reasons for these. Firstly, it's to widen the area from which a tree can osmosize and get its nutrients and water from. Actually, probably that's the least important, or the secondary reason I should say. The main reason is that these buttress roots act as anchors or supports for the tree to grow incredibly tall. The concept here would be that if you can picture this like Jenga, if you take, everyone's done this, haven't they? They've taken the individual Jenga blocks and built as high as they possibly can with a tower, and then you get to about 15 or 16 blocks, and the Jenga tower will begin to move to the left and right and potentially fall over. Your buttress roots here are the idea that the tree, without those buttress roots, would not be supported well enough, and although there isn't a great deal of wind in the tropical rainforest, any wind or potentially flood would potentially push that tree over. So buttress roots are there to anchor the tree in the ground. The reason why they need that is the tree needs to be as tall as possible to make sure it reaches the sunlight. It cannot afford to be any shorter than it is, otherwise it has the potential to be shaded by the level of competition around this tree. So buttress roots are to anchor, to encourage or to stabilise the tree to make sure it can grow big enough to get the sunlight to photosynthesize and therefore survive. Heavy seeds, I'll go through quickly as well. These are Solomon Island walnuts that you can see here. Very, very heavy seed. The reason why seeds need to be heavy is that they have the ability then to punch through the dense leaf litter that you'd find on the ground here. Without this in place, the seeds would land on the surface of the leaves themselves and be eaten by animals on the ground layer. Birds as an example, or boars. Wild boars would be another one that would eat those seeds. They have to be heavy to punch through the leaf litter to enable the seed to actually germinate and to actually grow itself. So heavy seeds, another useful adaptation there. The other three up on the board: thin, smooth bark, lianas and epiphytes. If you want me to go through those, come and see us down H7. I think those three would cover everything you'd actually need to know for this course. The other one, just quickly say, is large leaves. Large leaves to catch as much sunlight as possible. The reason why they need to be large is the likelihood is that the tree will be shaded, particularly if it's in the shrub layer, so it needs as big a leaf as possible to capture as much sunlight as it possibly can. Final three adaptations: lianas, epiphytes and bark. This might have been on the previous slide actually, but I will just go through these anyway. Start with lianas. Lianas are actually rooted in the ground. However, their strategy is to almost race to the top, and what they do is they use other trees as their anchor or support to get up to a position where the plant themselves can actually then photosynthesize, minus the need to actually put a tree trunk down. Very, very clever adaptation, all based off this idea of competition, because quite simply, if the plant had tried to grow as a trunked tree, the likelihood is it would be shaded and therefore would not survive. It would not get enough photosynthesis and die. As a result, it puts everything into rapid vertical growth simply because of the rate of competition, and it will coil around other trees as its anchor to grow to the top, to flower or to leaf there to try and survive that way. Epiphytes slightly different. These are parasitic plants that actually don't get their moisture themselves from from the ground. They actually get the moisture from the air around them, or actually even from the stems of other trees. Again, the concept is here that the amount of competition means growing on the ground layer is so difficult that actually these plants essentially cheat and start from the top, so they can ensure that they can survive and photosynthesize. I should point out both of these lianas and epiphytes will actually have the long-term effect of potentially pulling down or weighing down the larger emergent or canopy layer trees. So in the long run, these actually may well cause the larger tree itself to fall down, which actually then gives trees in the shrub layer, or actually at the ground layer at that point, the chance to potentially grow. Final one, thin smooth bark. We're just focused on the thin version here, or the thin point. Thin smooth bark, which can also be linked to no lower branches. The idea is you put the tree puts absolutely everything into growing as vertically, as rapidly as it possibly can to ensure it can photosynthesize. Trees in this country generally have lower lower branches, I should say. And the reason for that is that there isn't that level of competition as there is in the tropical rainforest. You want to put everything possible into growing vertically. If you grow horizontally, the likelihood is actually those branches at the lower layer will be shaded, so you grow vertically as rapidly as you possibly can. And you may also notice there that it is very, very thin. You don't want to put too much work or effort into a large trunk at this point. This is an early growth mechanism to grow as quickly as you possibly can to reach the canopy layer. Right, from the previous AERS diagram, we had a little point there, the vegetation effects on the climate. The tree itself will transpire as it grows and will release water vapour, and also water will be evaporated from the leaves itself, and as a result it literally has the impact that actually you have water vapour rising from the tropical rainforest, which will then cool, condense, form clouds, and actually therefore precipitate again. Furthermore, another way that vegetation influences the water cycle here is through the roots. They will osmosize huge amounts of water to fuel their rapid growth, and as a result that water can then be transpired out of the tree as well. Tropical rainforest animals, as probably unsurprisingly, most animals are found in the canopy, e.g. monkeys, well adapted living in trees, I'm sure you're aware, incredible balance, a prehensile tail as examples. Most fruits are found in the canopy layer. Examples that grow all year would be figs, and as a result the monkeys, as an example, will live there as they always have a constant source of food. However, that's not the only place that animals live. Wild boars will live on the forest floor, eating seeds and berries that fail to punch their way through the leaf litter. Hopefully the concept here is that you have a whole range of different habitats created here on the basis, and linked, I should say, to the vegetation that is here in place. There are very few large animals found in the tropical rainforest simply because the vegetation is so dense. They find it very hard to move around the area, and furthermore very hard to find cover, if you will, when they're hunting their prey. Little section here, just be aware of the Solomon Island tree frog. This is, I believe, at first looks, there are 5 frogs here which hide within the leaf litter, and what these frogs will eat is your insects that are attracted to the vegetation on the ground. They will eat those. Very, very well adapted. Obviously camouflage here is a fantastic adaptation these animals will have, and they are adapted to the forest floor. There are other tree frogs within the Solomon Islands that are also adapted to live on the lower branches of any trees that exist, and also in the canopy layer as well. Tropical rainforest soils and rapid nutrient cycling. This is the relatively easy part, if I'm being honest. Trees will shed leaves all year round, as there aren't really seasons as such. There is always moisture and sunlight available, even if it's much less in June or July within Manaus. Trees will shed their leaves all year. As a result of that, you have a constant leaf litter in the tropical rainforest, but the vegetation actually decomposes very rapidly. The reason for this, remember, is you've got that warm and wet climate. That means the decomposers work very quickly to rapidly decompose that. This provides you rich nutrients which will be absorbed by the plants through their shallow roots. However, these nutrients are really in high demand, so they do not stay in the soil for very long at all. So there you go, nutrients enter the soil surface, don't get a chance to sink in because they are so demanded by the range of trees here in the tropical rainforest. The shallow roots quickly take up the nutrients, it fuels that rapid growth cycle. Now, something that isn't actually in here is that the animal feces dropped to the ground are also going to add nutrients to the soil, but in exactly the same fashion as the leaves themselves. They're going to be broken down incredibly quickly due to the warm, wet conditions your decomposers get to work in. If you remove this vegetation, the heavy rainfall will quickly dissolve and carry away any nutrients. Obviously, at the moment, the rainfall is being intercepted by these trees. If you took that away, the nutrients can be what's called leached or washed away, eroded, if you will, from the surface very quickly. And actually, what that leaves behind is a very infertile, iron-rich, red-coloured soil, which is called a latosol, Latosol, and the rain itself will erode the soil away. It therefore means this is a very delicate balance in the tropical rainforest. Just to finish off, it's a little introduction, 20-minute thing on the tropical rainforest. The AERS diagram, just to finish on here. Hopefully this video has shown you more of the links between all of these different parts of a biome or an ecosystem, in this case within the tropical rainforest. Come and see us down in H7. We've just recently done an assessment on this, so it would be good to recap this further as it's fresh in the memory.